2.5 billions of years ago, something horrible happened. Cyanobacteria started to do photosynthesis, which meant that they were producing something to eat and were ejecting a poison into the world. This poison in German is called Sauerstoff, sour substance, oxygen. Due to this huge catastrophe, 98% of all the species which were alive 2.5 billions of years ago went extinct. They died out. They vanished from Earth. 2% survived. Some of them were our ancestors, and some of them survived although oxygen was a dramatic poison for them. These organisms which survived this great oxygenation event, as it is called, are magnetotactic bacteria. They are bacteria which by chance 2.5 billions of years ago were producing magnets with iron, with oxygen, with sulfur, and they had these magnets in their body, and because of the magnetic field lines of the Earth, the bacteria started to orient along the magnetic field lines of the Earth. When they switched on their flagellum, they went down into the region where you have sludge conditions, where you have no oxygen. And they survived there. The message from this long time ago is sometimes huge catastrophes open up a completely new ecosystem, a completely new possibility to survive in this world. And even nowadays, we still have magnetotactic bacteria, so if you want to go and hunt for them, go to the sludge where it smells horrible, where it smells like sulfur, and you will find the survivors from this big catastrophe so long ago. Nowadays, we are facing catastrophes on many levels. Today's four horsemen of the apocalypse are conflicts, climate change, resources and pollution, and politics. When it comes to conflicts, whenever individuals or species live together, conflicts arise. This is normal. However, there are light figures in our history, like Nobel Prize winner Albert Schweitzer, who introduced a beautiful concept. In German, it's called Ehrfurcht vor dem Leben, reverence for life. And in a nutshell, this Ehrfurcht vor dem Leben, this reverence for life, means I am life who wants to live among life which wants to live. And if we live along these lines of this beautiful concept, it helps a lot towards a good future. So we can potentially construct the bridge between plants and animals and our own world and prepare it for a good future for all. The second huge problem we are facing is climate change. As you all know, a couple of years, a couple of decades, a couple of hundreds of years ago, nature was viewed as a source of resources and as a place where you could dump everything. When I was a child, when I went to the forest, there were refrigerators in the forest and cars in the forest. So people just used nature as a dump for our waste. And this was the beginning of a horrible development where we are currently experiencing the first instances of this catastrophe, which is starting to grow more and more in the next years to come. Because even if we develop good solutions nowadays, it's like steering a big ship. If you turn the wheel, the ship doesn't change course immediately. It takes some time. So the catastrophes will grow over the next years. And then, hopefully, our measures will start to take effect. Resources and pollution is the next big problem that we are going to face and that we are facing in many regions of the world currently. What you can see here on this slide on the left side is a representation of how we are doing it nowadays. So we are extracting the materials that we need somewhere. We are transporting them for thousands of kilometers. Then we're bringing them to a factory. Then we are refining them. Then we are pressing them into shape. Then we use them, and then we dispose of them. When we look at living nature, it's completely different. The things are growing with local materials, under ambient conditions, no high temperature, no toxic chemicals, with water-based chemistry, in functional shape, like the sunflowers you can see on the slide, and at the end of their use, they either rot or they can be eaten by somebody else. Pollution is a big problem when it comes to electronic waste, when it comes to textile waste, when it comes to toxic waste, and increasingly we have to deal with this problem, and it's not enough to sell our garbage to Malaysia or Indonesia or to the Atacama Desert. I don't know if you know these photographs of the Atacama Desert, where you have in the desert our fast fashion remnants. Some of them have never been worn by anybody. So growing things in functional shape is a promising route for the future. And our work at the Vienna University of Technology is looking at this growth. And now I come back to this magnetotactic bacteria, which I showed you in the very first slide. So local materials, local iron, local metals, for example, can be accumulated by plants such as sunflowers. Sunflowers have the ability to bring copper and cadmium from polluted soil into their petals, so not into the fatty seeds, but into the petals. And when the petals are then burnt, they have a very high metal concentration, which we could use for further use. And not just sunflowers can collect metals. This is called phytomining. Phyto stands for plants, mining stands for mining. But there are 450 different plants which take metals from the soil, from the water, from the air. So just imagine if in the future we could grind down our electronic garbage from mobile phones, from beamers, from computers, and use plants to selectively take out the chemical elements that we need. So this is one of the approaches that we're doing at TU Vienna. And the advantage is there wouldn't be long transport, and we wouldn't need to have to negotiate with countries which are very doubtful the way they treat their workers, the way they treat their women, the way they treat life in general. But we could, with our local resources, take what we need. And chitin and keratin, which I also have on this slide, are our main current investigations. Chitin, you know from butterflies. Keratin, you know from your hairs. And also the horn of the rhinoceroses are made from keratin. And these are two substances which can relatively easily be produced, and simply due to structures, you can induce various functionalizations in them. So for example, high mechanical strength, like in porcupine quills, or beautiful coloration, like in butterflies, blue, green, iridescent coloration, which changes color with the viewing angle. Radiative cooling, passive radiative cooling. There are butterflies, there are ants in the Sahara who passively radiate heat into outer space. And one of my students is working on transferring these properties, which are based in the chitin structure, to chitin from shrimp shells, waste material, and to bring this to the facades of houses so that the houses in hot countries would radiate the heat to outer space, so would cool down and you wouldn't need to use any air condition. So that's one of our approaches. And growth is the last thing you can see here. Growth is absolutely fascinating. If you think about a tree starts from a little tiny seed, and mainly with substances from thin air, with some sunlight, with some water, with some local nutrients. From this tiny seed, it's growing into a big, beautiful tree, a programmable material. Wouldn't this be wonderful if we could transfer this to growing our technology, to growing our devices exactly where we need them? I need the TEDx letters here, so I grow them exactly here. I don't transport them here with a lorry. And our approach is to think about this growth and to start to be active in this area of growth is something which some of you might have seen when you were hiking in the forest. It's plant galls. A plant gall is a structure on a plant which is induced by a tiny little wasp which comes and injects some chemicals and which convinces the plant to grow a house for the baby of this insect. Gallwespen, gall wasps in English. And we are now trying to start to understand which switches need to be switched to grow things exactly in the shape that we need. Because these houses for the gall wasp babies, they have an inner layer which is sugary, so the wasp larvae, they eat the sugar layer, and then when they are all eaten, it's reproduced by the plant. It has an exit hole, and it's very beautiful and a safe space for the wasp baby to develop. And so we want to grow things like, for example, a champagne glass made from wood. And the advantage would be that you wouldn't have to cut down the tree. You would convince it to grow the things on the side. So that's one of the things that we are dealing with in our growth studies. And now I come to the last problem that I would like to shortly touch upon. It's politics. We all see a global going down of democracies in the world. We have more and more problems with states which cannot be called real democracies anymore. And one of the problems behind this is that people try to vote for what they believe is the best. And they don't vote for the best, but they vote for what they believe it is the best. And now in our interconnected society, it's very easy to induce false beliefs in people. So democracies are going down, votes are flawed currently in so many countries, and I think also here is a solution, because due to the interconnectedness of our current world, I think new structures are going to develop, how we are interacting, how we are securing that our interests are represented by the governments. And I cannot say how the political system of the future will look like, but similarly, like the magnetotactic bacteria found a way out to survive, I'm sure that also we will find a way to come out of this conundrum in politics. So to sum up, I think there is hope, but I think this hope can only be opened up to all of us if we work together and if we are convinced that, stepping together towards a positive future is possible and is doable, and we all contribute to it.